All right, we now come to the final lecture in our initial series on introductory virology. This lecture is a freebie. At this point, there's nothing on any exam from it, so you can just relax. So we're going to talk about these items on this list in order. The real lesson here is that while in this age of COVID-19 we tend to take a rather dim view of viruses in general, it's the case that many of them are actually extremely useful or can be engineered to be extremely useful, as we're going to see. So taking these in order, certain viruses can be used as biopesticides. So let's say you've got a pest insect that you want to get rid of. You could use chemicals, but those are notoriously unspecific. They'll be toxic for any insect, including beneficial ones, so not a good idea. Viruses, on the other hand, are host specific. So if you have a virus that will infect, let's say, the tent caterpillar, that's all it's going to infect. One of the viruses that is really useful in this context is called a baculovirus. So these are very effective. One of the tricks that this group of viruses, and there are two other virus families that has come across that same strategy. And what they do is the mature virions become embedded in large protein crystals. And in the case of baculoviruses, the crystal, and you can see part of one here, right in the center, the crystal consists of multiple copies of a single polypeptide called polyhedron. So you'll note that this virus has an envelope, right? So if you wanted to spray this virus over a crop or a forest against some pest insect, you would probably apply it from an airplane, and you would probably force the virus out at high speed through a nozzle. Well, that's going to kill the virus, because the shear forces will strip the membrane off the virus and inactivate it. But if the virions are embedded in a protein crystal, the shear forces will have no effect. So the virions are protected. So that means you can use the embedded form of the virus as a very effective pesticide. The other thing to note about polyhedron, as I've implied, is that it's made in massive amounts, as we will see in the next slide. This brings us to the subject of recombinant vaccines. So when you get a shot for Hep B, the Hep B antigen will most likely have been made in recombinant yeast cells. So you can use expression vectors to make a recombinant protein and then use that protein as an antigen to facilitate the induction of an immune response. The other way to go is to take a non-pathogenic virus, like say vaccinia, or cytomegalovirus in some cases, and engineer this virus to express one or more viral antigens against which you want to induce an immune response. So this has been done quite effectively in some cases. So monkeys, for example, are infected with SIV, which is a simian immunodeficiency virus. So you can engineer a monkey cytomegalovirus to express several of the SIV antigens and then inoculate monkeys with that recombinant cytomegalovirus. The virus will cause a low-grade infection and express the SIV antigens, and the monkeys will mount an immune response against that virus. And in recent research, monkeys so vaccinated were completely protected against an SIV infection, which would otherwise have been quite lethal. Okay. We now come to the subject of phage therapy, and that means using bacteriophage, bacterial viruses, to protect against or attack a pest bacterium. So in this particular slide, this has been done. So you've got two tomato plants here. Both of them have been sprayed with a bacterial pathogen. The one on the right was also sprayed with a bacteriophage specific for that pathogen. And you can see the tomato on the right is looking pretty good. Now this can also be used in the context of oral biofilms, as the next slide will show you. So this is a diagrammatic representation of an oral biofilm, like dental plaque. And in B, antibiotics have been applied, but they don't penetrate biofilms very well. In diagram C, the biofilm has been treated with one or more bacteriophage specific for bacterial elements in the biofilm, and you can see that many of the bacteria have been killed, and this, of course, used in combination with antibiotics could in theory be quite effective. I'm a big fan of phage therapy, and I can see the day coming when, instead of gargling with some toxic compound that affects bacteria, you'll gargle with a cocktail of bacteriophage. This would not surprise me in the least. And the next slide will show you something relevant and quite interesting, I think. So what you're looking at here is a bacterium with a very thick capsule. And bacterial capsules typically consist of polysaccharides, and these are very common in dental biofilms. If you've got a virus that infects this type of bacterium, it has to get through the capsule. And that means that on its surface there must be an enzyme specific for that capsular polysaccharide and able to digest it. And in that manner, the bacteriophage particle can eat its way through the capsule and reach the surface of the bacterium, at which point there will be another viral protein on the surface which will recognize a different receptor on the bacterial cell. And you can see a couple of phage here that have eaten their way through the capsule. So these phage and other phage can be engineered to express enzymes like this, enzymes which would digest one or more components of a bacterial biofilm. Okay, so I can see some hope down the road for engineering bacteriophage to do just that. In the next 3 slides, provide some reference materials relating to phage therapy used against Enterococcus faecalis. This, despite its name, is a common oral bacterium. It can infect root canals, and it's hard to get rid of. It's able to make biofilms. It's just a nasty bug. And sometimes it gets into the bloodstream and can cause systemic infections. So it's not a nice organism. But anybody who's interested in this should feel free to access this literature. This work was published, I think, in May of 2019, so it's very recent. It's a fascinating story, and I think we're going to see more stories like this coming up. So what happened here was there was a 15-year-old girl with cystic fibrosis, and patients of this sort often have lung transplants. She had a double lung transplant. And at the time, I don't think the physician realized that she also had a Mycobacterium abscessus infection. So if you get, if you have major surgery and you have this organism, you're going to die. And the first page of this paper has a horrific description of the condition she was in. So she was going to die. And her mother kind of came to the rescue and approached the physician and said, I've heard that you can use bacterial viruses against bacterial pathogens. And of course the physician, who was a transplant physician, knew nothing about this, but said she would look into it. And that led her to a guy named Graham Hatfull, and you can see his name and just below the title. And he had been working for years with a consortium of schools developing a laboratory exercise for first-year students. And what they were doing was pulling bacteriophages out of the soil for an organism called Mycobacterium smegmatis. And so he looked into his collection. I think he had about 10,000 different phage for Mycobacterium smegmatis, and he asked the question, maybe some of these will infect abscesses. And he found 3 that did. And so the girl was given a cocktail of 3 of these phage and was cured. We now come to the subject of gene therapy. So the ZAP protein, ZAP means zinc antiviral, or zinc binding antiviral protein. This is another type of innate immunity. And this pathway, as I suggested earlier, is deficient in at least 50% of all human tumors. And so if you can find a wild-type virus that is sensitive to ZAP, it won't replicate in normal cells, but should replicate preferentially in tumor cells. And in China, a few years ago, a mosquito virus was isolated that did just that and was very good at replicating in tumors and not in normal tissues. All right, so those are examples of using wild-type virus to destroy tumor cells because the tumor cells are deficient in some element of innate immunity. The other approach in terms of developing an oncolytic viral therapy is to take a virus and engineer it to be sensitive to something that's going on in tumor cells that is not going on in control cells. The last slide provides a very good example of that, and I'm not going to say much about it. Basically, this was done in Japan a few years ago, and it's taking advantage of the fact that in tumor cells there is an upregulation of telomerase activity. So if you engineer a virus to have a promoter that's sensitive to whatever is upregulating telomerase activity, then the virus becomes, viral replication becomes upregulated as well, and this will happen exclusively, one hopes, in tumor cells and not in surrounding control cells. All right, we're done with this particular lecture, and the next 2 or 2.5 lectures will be on the oral virome.